very good.
So I think we can start. You have 25 plus 5 minutes for questions. Please go ahead.
Okay, thank you very much. I'm giving this talk on very short notice. We learned about this yesterday, actually. So we had a speaker from the Bell side, Umberto Tamponi, but unfortunately he became sick. So Todd Pedler, who is also very much a bottomonium expert. He was already in Clio, and he was very much involved in ETA B at Bell some years back. But we learned yesterday that also he cannot give this talk. So we communicated with the speakers board. We have very strict rules in Bell 2 also, what results can be presented and which one not. And so we needed a rehearsal, but that was not possible on short term. So what we did is, in communication with the speakers board, Elisabetta was asking, so we are allowed to show a few slides that have been shown before. And that's exactly what I'm going to do. So half of my slides actually have been shown by me on a workshop back in November that Ahmed was organizing. So yeah, I included just a few slides about Bell 2 as a reminder. It was shown by Yunao last week, but maybe not everybody attended. So of course we have the upgrade of Bell, called Bell 2, running already since almost 3 years now, with a lot of upgraded detectors. In particular, for example, we have a vertex resolution, which is now something like a factor 2 better than Bell, which was already demonstrated. So the data taking is ongoing as we speak. So the numbers already changed from last week compared to the ones that Yunao has been showing. So as of yesterday evening, we were recording 259 inverse femtobarn, which is about 30% of Bell and about 55% of Babar. So in BB bar pairs, this is always one inverse femtobarn is about 1.1 million pairs. So the peak luminosity just around Christmas time already reached 3.81 times 10 to the 34, which is 80% higher than the previous world record. And you always have to compare to 1 times 10 to the 34, which was the original design luminosity. So we are almost a factor 4 higher than the original design 20 years ago. So of course we have the pandemic situation, but we changed everything to data taking with shifts, virtual, digital shifts from wherever you are located, with quite high efficiency, 90% of data taking delivered data that we can actually use for analysis. We have an upcoming long shutdown for replacing part of the pixel detector and also of the time of propagation counter, which is the Cherenkov counter. And that can be seen here in the plot bottom right. So the yellow area is the long shutdown. And we will be expecting something around 500 inverse femtobarns. So not quite full 100% of the Bell data set, but something like, let's say, 1-to-1, and then we can try to do combined analysis of 50-50. So bottomonium, how can we access? So at Bell, what we are doing is mainly a plus and minus collision, but I come back to that point, how we can populate the upsilon states, for example. Just as a reminder, charmonium and bottomonium are a little bit different, because in bottomonium case, some of the states, like the 2p states and also the d-wave states, are below the threshold, and that's different from charmonium, where they are all above. So that makes them narrow. So compared to LHC, in LHC there's completely different production mechanism. So it's a prompt production of charmonium, which brings really limitations to them, as I will show, some of the states, like the Upsilon 5s, have never been seen at LHC so far. So some plans, what we are actually going to try at BEL2. So the spectrum of Upsilon resonances, which means here our beam energy can be adjusted. So we are moving to the peaks. Yeah, it's a bit different from the usual operation. So in usual beam meson physics, we are sitting on the Upsilon 5s, which is almost 100% decaying to BB bar. But for the bottomonium studies, we are changing the beam energies to 1s, 2s, 3s, or above to 5s and 6s. And these are here already some numbers from Bell and Babar. But here the table form. So these are the 6 states. That is basically our range for the adjustment of the beam energies. And the 3 colors are here the taken data sets of Bell, Babar in dark green and Clio in blue. And the blue lines are the cross section. So the scale of the cross section is here on the depicted on the right axis label. So the Upsilon 1s, for example, has the highest cross section by far, but they have been used for physics. For example, a search for invisible decays, dark matter decays. But for example, Babar never took data on the 1s, only Clio and Bell. For the other 2s, 3s, 4s, we have data sets from all experiments. And 5s and 6s above, only Bell has been doing so far. And I will show a little bit. So what BEL2 is planning then is in yellow. So we focus a bit more on the high mass regime. So 3s, 4s, and 5s and 6s, quite a lot is the plan. Because here is especially the 5s is probably where the exotic states are sitting. So for the 2s, the 3s, for example, the topics are lepton flavor violation, lepton universality violation, and the invisible decays that I mentioned also, because the 3s is also still below the beam bar threshold, the meson threshold. Deuteron formation by coalescence can be studied because the Upsilon states are decaying. So it's 3 gluons. That's why they are. You can actually produce hadronic final states up to really deuterons. But the way we are identifying this is actually anti-deuterons. Yeah, because the background, like deuterons, coming a lot from the beam pipe interactions, but anti-deuterons can be only created in the interaction, in the collision. Hyperons production and germania, also in Upsilon decays, dibarion searches have also been done already at Bell. Here the H dibarion, for example, there's one Bell paper. And in radiative transitions precision, QCD. Upsilon 4s is our main source of ISR, but that will be covered in the next talk, after my talk. Here, spin singlet, the eta B, for example, show up in Upsilon 4s decays. And the increased data set here will be actually also enable us to do eta B in gamma decays. 5s, 6s, as I mentioned, is really the playground of the exotica. So here will be a lot of threshold scans and then exploration. Also here, eta B, for example, or HB, that have also been seen in Upsilon 5s decays, but that I only have in my backup slides if someone is interested. And the scans, of course, then in high statistics. Some results from BEL2, so these are really already data that have been shown by Brian Fulsom, one of our bottomonium conveners. on the Hadron conference last year. And what you see here is the epsilon NS transitions in data at Bell 2 already. So the 2s to 1s, 3s to 1s, 4s to 1s. I will show later one plot about the epsilon 5s pi transitions. That's why I show these here. And this has been based on 72 inverse femtobarn. And as I mentioned, we already have 295 right now. It just takes some time, the data processing and so on, until the data become available then as results. So, however, we have two ways of production, and that's why I would also like to mention again. So we have the E plus, E minus directly sitting on the resonance, producing the epsilon states, because it's 1 minus minus, that's why it works. But we can see, of course, then also the epsilon ns, the lower lying epsilon ns in the pi transitions. Why is that important? Here's one of the Bell papers. These transitions actually are not alike. It's not that they look all the same, because the pi mass spectra, if you look, for example, so this is here 2s to 1s. On the top right is 3s to 1s. On the bottom left, 4s to 1s, and then on the bottom right, 4s to 2s. And you see that the pi mass spectra look quite different. For example, here the 4s to 2s, you see here also the efficiency is depicted. Yeah, it's a blue line. So you can see here that in the low mass region here, especially, is very much populated, and the efficiency is very small. So that's a very, here with these large error bars, it's a very striking signal at low masses. Yeah, which, for example, in the 2s to 1s does not show up. Okay. So that was the plan, what we are going to try at Bell 2, and now a selected topic, the so-called YB scan. So one of these exotic scans. So the and that goes back to the epsilon 5s. The epsilon 5s is one of these states. To my knowledge, at least, it has never been seen at LHC. So that's something really, is an advantage for Bell 2. And it's all started with the observation that this pi transition, the epsilon 5s to epsilon ns, where n is here the 1 or 2 pi, is too large by factor 1000. It's an enormously striking signal, and that is can be seen here on the bottom. So you have here the delta m is the mu pi. So the mu then is reconstructing the epsilon state, the initial minus the final state, and then you have the transitions here, 3s to 2s, 4s to 2s, and 5s to 2s. So on the left side is the 2s, and on the right hand side is the 1s. So 2s to 1s, 3s to 1s, 4s. And you see that here, let's look on the right bottom. So 1s. 2s to 1s is that signal here. Then 3s to 1s goes down. 4s to 1s is almost not visible. And then 5s to 1s goes up enormously. Yeah, and that's that factor 1000. Much more than expected, and that, of course, always raised the question: is the 5s exotic itself? Moreover, in the decays, in this enormous data set, of course, that we have then for the 5s, the ZB states were observed. So two of them. Here's only the decay in HB 1p pi, but we have these signals in 5 different decay channels. And also, to my knowledge, the ZB states have never been seen at LHC. So it's also something that really Bell can do very nicely. And everybody remembers probably very peculiar properties here in the decays. The spin flip is not suppressed. And So to continue the story, a new state was observed called the YB at 10,750. And that new state, YB, has been seen below the 5S, yeah, in scans. So that region was scanned at Bell some years back with about 1 inverse femtobarn only at each of the scan points. Yeah, and that yielded a structure. So this is here 1s pi pi, 2s pi pi, 3s pi pi again in all the 3 channels. And the parameters of that state were determined as around 10,750 with a width, Bright-Wigner width of 35 MeV. And then there was an analysis, not by the collaborations, not by Babar or Bell, but by a few authors, Dong et al., who took the publicly available data from these scans, fine scans also from Babar, and that you can see here in the bottom right plot. And in that, there seems to be destructive interference appearing at this point, which reminds you of the Y4260. So Dong et al., I think, if I remember correctly, also Shangzhen, who is connected here, is one of the authors of this paper. So if we are discussing maybe later. So that's intriguing situation, somewhat similar to the Y4260. So the new scan did already happen in November. So the scan started 11th of November. And so with 4 scan points in total, that can be seen here on the bottom left with the dashed lines, where the 10,750 is the orange line, and the red lines is the additional 3 scan points. So on the maximum, the plan was something like 10 inverse femtobarn, and then on the other ones, something like 1 inverse femtobarn. So, and then what can you do with the data? And that's ongoing, but of course it's takes some time, the analysis. So the prediction in transitions of that state to 1s pi pi is actually a paper by Ahmed Mayani and co-authors from 2020. And if you investigate, for example, here the pi pi mass spectrum, and the green plot here is a prediction from that paper, which I compare to the plot here, epsilon4 to epsilon1 pi pi, down here with the same scale. So the 0.3 is here, the 1.2 is here. Then the idea is, if that's really a tetraquark, then certain components such as scalar F0 states should be dominant here, which they are not in conventional charmonium decays like the 4s to 1s pi pi. So, but we can even do more. We can do checking in so unfolding BB bar star, and B star bar. So, and depending on this, if this is a tetraquark or is a conventional bottomonium state, that ratios should be somewhat different. Yeah, the reason is that if you have a 4-quark state, then the light QQ bar pair is already in the system. Yeah, inherently already there. While if you have the bottomonium only, then the QQ bar light pair has to be created with a vacuum with the quantum numbers of the vacuum, QCD vacuum, and then these ratios change. And the red line depicts where we would be expecting the peak position and where was our scan point, and then we could compare. So that brings me already to the summary. So we have a established program at Bell 2 we will do scans in that region, changing the accelerator energy. And the 6S is, of course, it's a very intriguing case, and it's under discussion how much data we will be taking there, because it's always a little bit competition. You just have to decide where you spend the time. Yeah, because also searching for new physics in decays is an important topic, or searching for dark matter or these things. So it's a discussion in the collaboration where to put priorities. The plan, if you are interested, here is this archive. It's approved with 50 scan points and 10 inverse femtobahn each point, which compared to Bell is something like factor 10 per each scan point, with an average spring precision of 1 MeV. And that's all I want to show today. Thank you very much.
Thank you for the talk. And now is time for question. Let's see if there is some hand up or people who is willing to ask something. Oh, many hands. Let's start in order. I see Christoph.
I thought Claudia was a little quicker, but
okay, guys, I don't know, because I see 3 hands up. So
can you go to page 7?
First. Ladies first.
Claudia. Oh, ladies first is fine.
Yeah, thank you. No, my first question is probably something that we should not ask ourselves. If the new structure that you see behaves more like a bottomonium state than the 5S, actually, because the 5S is way more unusual than the new states that you are looking at. So maybe, I don't know, how sound is the identification of the 5S as?
Yeah, it's always a bit tricky. I mean,
yeah, that's more of a comment, and we all know that it's not an easy task. But anyway, that's very, very good to see new data coming in this region where we do not understand much of what's going on. So it's really nice. As a former Babar member, and actually still a Babar member, because we are still producing data, it's very good to see this very nice data coming out of Bell 2.
Yeah.
Congratulations, and looking forward for the next new data that you're putting out.
Yeah, I will try to pass the congratulations, because I'm not the main person involved here. I'm just the
No, I know Umberto and Todd, so I'm very happy to see that they have new data to crunch.
Yeah.
Unfortunately, Roberto cannot join the discussion today. I was just talking to him this morning. Otherwise, he would have very interesting, whatever input he could give to the discussion also in the afternoon. Sorry, I interrupted you.
No, I was just going to add that the tricky part here is in the ratios, of course, that the ratios you see here, they are fluctuating very much depending on the energy where you sit. And already for the 5S, these ratios are, if you compare to heavy quark spin symmetry, they are off. Okay, so for example, in the Upsilon 5S, here the B star bar is completely dominating. It's something like 90 or 93% or something. So it's
that's really something which in a plus-minus machine can do the best, because you can really disentangle and measure separately all contributions, both to the harmonium transition and those anomalous transition to the ZB and everything else, and BS bar, BS star, whatever. So you will have the possibility to perform really a very good set of measurements in this complicated region, where I'm really looking forward to see them.
Thank you, Claudia.
That's all for me.
Now, Christoph.
Okay, thanks a lot. Can you go to page 17, please? Here you said that the F0 states do not contribute to regular charmonia in the double pion decays. This statement I don't understand. Pi-pi interactions are universal, and the pi-pi pair is in the 0++. And when you really go to this in page 17, when you look at the,
sorry, yeah, I was going.
Same spectrum was probably also on a different page. Actually, you see the effect of the F0980, right? Because you see when you look exactly at 1 GeV, you see a very strong change in how the spectrum looks. This you will never get without the F0980 playing a role. Therefore, this is really the usual subtle interplay of, say, the signal from the F0500, F0980. In this case, a little overruled by the effect that the leading order Carré perturbation theory predicts here two low energy constants that have a different m-pi-pi dependence. So with just two parameters and the final state interaction included, you get that spectrum, but you need the final state interaction. And I would be curious to see then really the spectra for this YB, because that will be telling, but the chiral structure is universal. Therefore, one still has two parameters, that's for sure. And one can adjust them and see how different they are in the different transitions.
Mm-hmm.
Right? And there's also some effect from the ZBs. They just appear as virtual states. Although that effect is small, it gets increasingly more, they get increasingly more important as one moves to heavier states. But they even have an impact on the Y3S transitions, although very mild. There was more a comment, thank you.
Okay, I was not, I think if I remember, Ahmed may correct me, okay, it's his paper anyway. So it's not only the F0980, but it's also here in the intermediate region. So the 0.6, where the scalar component gets stronger.
No, but the F0500 also plays a role. Therefore, when you look at the structure in the lower right plot, that the F0980 is basically digging into something big, is the F0500 underlying.
Okay.
It's only an interplay of the two low energy constants that suppress the left-hand corner.
Okay.
Thank you for your comment. Maybe we can continue this in the discussion. I see other two people wants to ask a question very shortly. Heinz.
Yes, thank you. I think it on page 10, you mentioned that you also can detect deuterons and possibly, oh, no, must have been, 9, yes. Deuteron formation and possibly dibaryon production. Does it mean you could look at dibaryons which are bound only, like possibly the bound H dibaryon, or can this also be dibaryon like the D star 2380, which is a delta-delta state and decays, of course, hadronically? Could you look for it on this reaction E plus and minus going to anti-deuteron and D star? What I suggested yesterday, would this be a possibility?
Actually, in the plan, there is to look for the Jaffe particle, you know, lambda bar, so the UDS hexaquark. This is what is in the plan. I don't know if there are other plans. Maybe Sören wants to comment if it is possible to look for these multi-pion states, such as what Heinz presented yesterday.
Yeah, so the anti-deuterons are not something new. So they have been seen by already by Clio, I think even by Argus and Bell and Barbar both. So it's just the matter of statistics. So it was in the beginning of it was surprising where they are coming from. So they are really coming from upsilon decays, yeah. And but so far, all the analyses have been inclusive. So only detecting the anti-deuteron and not checking what is on the other side.
Okay, yeah.
That would be the next step. And I don't know if anyone calculated ever rates how much to expect, but I agree, it would be very interesting. The H-dye baryon, we have one Bell paper, and right now I think is Titi still here? It's the group of Concertina doing this, and I think the final state is lambda lambda bar, if I'm not mistaken.
Yeah, this is what people in Bell 2 actually in this moment are after, in this really the group of minds which is working on this.
Okay.
There are, of course, other possibilities that one can explore, but let's say the focus is on that particle. There is actually an upper limit, which I think Babar set up. Okay, but we can come back to this during the discussion. Otherwise, now it becomes too long. There is still one person who wants to ask a question, and I happily see students want to ask a question. Dimitro.
Yes, I would like to ask two questions actually, but they're very simple and short, I believe. The first is rather general. I remember that on Tuesday when Lorenzo was presenting an overview of what LHC is doing today, there were several interesting search for exotics in the decays of excited BS mesons, which was not possible obviously in Bell because the energy of 5s resonance was not enough. So I'm wondering whether this will be now possible with Upsilon 6s data. Will Bell be competitive in this field?
I don't know, Dimitro, I don't know.
For sure is more data. I mean, we add the data to all the Upsilon and S. I mean, more you have, better it is, because the process that you are looking for is the S bar star, whatever, is in the continuum is quite a rare process. So you need the data. So more data you have, better it is. After another thing, you are using one Upsilon 1s, 2s, 3s, 4s, 5s. And if you have also the data of Upsilon 6s, is just more data that you can look for because it's compatible with the invariant mass that you are looking for.
Yeah, I agree that in our case, that the more data we have, the better. But I was particularly interested in these decays of BS star or BS double star decays where Bell could not do anything because we didn't get these decays because of lack of energy. So I was wondering if 6S can help with this. But anyway, the second question is technical about the pixel detector that you mentioned during this summer long-term long shutdown. Will there be a second layer of the detector installed or it will be something different?
Yes, second layer, but it's not that you can just add the second layer. You have to replace the whole pixel detector, unfortunately. So
yeah, of course. Yeah. Okay, thank you.
So it's 6 new layers that are going in.
No, just the inner two.
And the inner two, okay, extract, so only the first two. Okay, then it is.
As far as I know, maybe they also want to replace some of the modules of the strip detector, but yeah.
Okay, so it's the two inner layer for the pixel detector. Okay.
That for sure, yeah.
Okay, thank you.
Okay, thank you everybody. And I think we have to move to the next talk, which is the last talk of the day. Shuyao Gao, are you ready?
Can you hear me?